Buenas tardes, espero que hayan disfrutado del coffee break. A continuación tenemos a la doctora Anna Fontcuberta y Morral, profesora en Ciencia e Ingeniería de Materiales y Física en la EPFL, y a partir de enero la primera presidenta la primera mujer presidenta de la universidad. Preside el Comité Especializado de Cooperación Internacional en la Fundación Suiza de Ciencia Nacional. Ha recibido varios premios destacados, como la beca de excelencia Marie Curie y el premio EPS Emmy Noether. En su ponencia, Using Nanotechnology to Enable Quantum Technologies and Solar Energy Conversion, nos dará una visión general sobre cómo la nanotecnología permite aplicaciones avanzadas de la tecnología de semiconductores. Muchas gracias. Un fuerte aplauso.
Muchas gracias por la introducción. Ha habido muchos chistes por aquí de físicos y es la primera conferencia que oigo chistes, pues voy a intentar. Es una cosa que no he hecho nunca, pero voy a intentar. Y dice que van dos italianos a un restaurante y dice, ¿lo sabéis ya? ¿Lo sabéis ya? Pues ya está. ¿No lo sabéis? Ah, vale. Pues se van a un restaurante y se oye, ¡pum!, una explosión. ¿Qué pasó? Pues que se pidieron un pasty y un antipasti. Esto es solo para físicos, ¿eh? Vale. Es muy malo, ya lo sé. Vale. Voy a hacer la presentación en inglés porque no sé si tengo que hablar en español, como no lo hago nunca, porque me marché de país hace 26 años, me parece que tardaríamos 10 horas más y prefiero hacerlo en inglés, así vamos más a un paso más acelerado. So I'm going to talk about nanotechnology and how nanotechnology can help have new materials and how these materials can be used for something good. And before I start, I would like to ask you a question again. So have you ever wondered what all these people have in common? And have you ever wondered what these people have in common with you? Or could have in common with you? I think it's because these people are people that wish the best for humanity. They have their own vision and they bring it to the end with all their own energy. And you may like it or not, but they really believe in themselves and believe in what they can do to society and for all of us. And this is in all of you. You all have different qualities, and these qualities can be put for something greater, something good. Maybe we all not do rockets, we do something else, but we can imagine what it is. So I'm going to start the talk by telling something that you all know, but I'll give you maybe some arguments that you haven't seen. And next time you have a discussion with someone that tells you that global warming doesn't exist. And it's, oh, we have had temperatures high and low so often. So I'll present you a graph. So this graph, you see, so here the bottom axis is years, and it's many, many years. I think it's, years before present, so many years. And you correlate the temperature, average temperature in the atmosphere, with the average composition in terms of CO2. So people that say that temperature were up and down, and in the history of the Earth, it's correct. You can see that the temperatures go up and down, and maybe even 10, 12 degrees. This is correct. What you can also see, there's a direct correlation with the concentration of CO2 in the atmosphere. And so we can see that if we increase the percentage of CO2 in the atmosphere, we're gonna get an increase in temperature. There is no other way around this. And this is thermodynamics. It's about the reflectivity of the atmosphere in terms of the radiation that comes from the sun, but there's nothing to it. And you can see here, there is a very straight line because it's a very short time. You see here, in a very short time, the amount of CO2 is skyrocketing. And this is what's gonna happen to us. We're gonna all fry like an egg. You can see here how, since invention we have the Industrial Revolution, and it's been very good for us. It's been good. It's brought a lot of progress, and we all don't want to go back to live in 1750. At least I don't want to. But you see how we have increased the emissions in CO2. And this is what now we have to repair. We need to try to remove the CO2 from the atmosphere and stop emitting. So in my own little capacities and what I think about how I can contribute, the thinking is that in my laboratory, I want to create materials that can enable more efficient electronics. And today, I believe this can be achieved, not today, but in maybe 10 or 20 years, it's going to be quantum computers. Quantum computers are going to be computers that are going to enable calculations that today would require so many computers that we cannot build them. So this is what's going to be the first talk of my talk. So what are the materials that can enable quantum computing or quantum technologies? The second part is, if we want to stop emitting CO2, we need to stop burning fuels. And this we have to do by increasing the number of renewable energy we have. There are many renewable energies, and we need all of them. And one of them is solar panels. There's a lot of solar panels in the roofs, and we have more and more production. What I'm going to talk about is thinking about what are the materials that maybe we can fabricate that don't exist today, that would be more efficient of the ones we have, and even cheaper. So that's what we do in research. We try to think not what we need today, not what we need tomorrow, but can we think about what we're going to need in 10 or 20 years so that we go towards that goal. And that's what we do here. And if the slide wants to change. Yeah. Okay. So this is the structure of my talk. I'll start talking about one-dimensional materials that can be used for quantum technologies, and I'll talk about two examples. And this is an example of where you see a crossed nanowire, and this is the base that's going to be used for some qubits, which are the bits that are made of quantum states. And here you have some electrons that have a spin. Sometimes we use the spin as a way of characterizing this qubit. Second part, I'm going to talk about new materials that enable energy harvesting. And this is, maybe you see that as far from physics, but any physical system would need some materials to be implemented. So I'll show you here our strategies to create these new materials, how we think about enabling them in the lab. So we use nanoscale technologies for this, and the people that in my lab and myself, we are passionate to see how we can guide atoms. We launch atoms on a surface, and our passion is to see how these atoms, how we can make it that they organize themselves in interesting structures. And here you see different places. You have freestanding gallium arsenide nanowires. You have some nanoscale pyramids. You have some kind of flakes that are obtained on graphene. You'll see more about these. And you have some networks of nanowires and some zigzag nanowires that are freestanding as well. So our laboratory, what we like to do and we excel is to really guide the atoms as we want so that they create these interesting structures. And these then interesting structures are useful for these applications. So today, hopefully at the end of the talk, you will learn a bit more how this is done and how you can create interesting structures at the nanoscale and for what they're good for. So this is the schematics of the machines we use. What you have here, it's called molecular beam epitaxy. You have, it's an ultra-high vacuum machine, so there is nothing inside. To create an even better vacuum, we have here some walls that are cold, and they have liquid nitrogen to make sure they're cold. So any atom that would be in the atmosphere there, as soon as it touches the wall, it stays there because it's so cold. So we have a very good vacuum, about 10 to the minus 12 bar. We then have here some cells that we liquefy or we sublimate, we evaporate or sublimate elements in a very controlled way. So we send some beams of very controlled quantities of atoms here, and the sample is heated. And what we like to do is to, in fact, prepare the surfaces in a way that the atoms do what we want. Another experiment that we have here is called metal organic vapor phase epitaxy. And in this case, we don't send the atoms directly of what is going to be the constituent, but we send in a heating tube. So it's a transparent tube that we heat with lamps. And we heat it here, and we send some gases that contain the elements we want to deposit. As soon as they are heated at the surface, they decompose, and they leave part of their molecule there, and that's how we create the atom. So we will use the two systems today to create the new materials. So you've seen these freestanding nanowires, and these freestanding nanowires are traditionally obtained freestanding, and you'll see later on why we stopped doing this freestanding structure, because even though they're beautiful, they are much more difficult to implement in devices. And how this works is that you start with a wafer, you make some holes, you have an oxide, and this oxide is like a it's a material that the atoms don't like at all. So when we send the atoms here, like for gallium arsenide, we would send arsenic, and gallium, the atoms will stick inside the holes, but they will not stick on the oxide. They really don't like it. The oxide is really a repellent for that. So if they're right there, they will walk around until they find this place here, and then they create the solid. If you have gallium, you will alloy it later with arsenic, creating gallium arsenide. And so what you have is you have the liquid gallium, the arsenic diffuses through it and creates gallium arsenide. It's like if you put too much sugar in your coffee, you know, it stops at some point being sweeter because there's too much, so it precipitates because you reach supersaturation of the coffee. So then it's the same here. We keep putting arsenic in the gallium droplet. At some point, it solidifies as gallium arsenide, and that's how you create a gallium arsenide nanowire. This is the sketch, and as usually when we design an experiment, whatever it is, in the sketch, it looks easy and straightforward, but when we go to the lab, that's another story. So this is, you see here the papers where we worked about this, and the first was in 2008, and it was not on silicon because it was too difficult. We started doing on silicon 2012. This is the first time we got some success, and it kind of doesn't look very beautiful, but we published this, and we were very happy. And from this to this, to have it completely ordered. Sí, sí. Okay. So in fact, to get them ordered, as you see here, it took, you see how many years? 7 years. And many other groups were trying to do the same thing, and we were all fighting against the first things. And it's only the physical understanding of what happens at the atoms to understand how to make them do what we want them to do that led us to get this beautiful array here that you see. So just to say research looks nice, shiny, it requires a lot of work. There's a lot of frustration in this. But as soon as it works, you're the happiest on earth. So how can we do nanowire? So you've seen we use a metal droplet to solidify material. This is a technique that has been used for many years. There's another way, is we can use this anti-sticking surface, like an oxide, and then you can have nanowires that go up, but you can also try to think about other shapes. So you put the anti-sticking surface on a substrate, you open some slits, nanoscale, because we want to do nanoscale materials, and then you hope that only you will have growth there because the atoms don't stick everywhere else. And this allows you to make the drawings in principle you want. But it doesn't work quite like this because these are crystals. So crystals have their preferences. So this starts with the quantum technology. Sorry, I went too fast. So I will tell you how to obtain these nanoscale wires in this selective area growth, that's the name of this. And the first motivation for this was to quantum technology that people put a lot of effort. In fact, Microsoft worked on this for many years, is to create what is called Majorana fermions. So Majorana fermions, they come from this physicist, Ettore Majorana. Ettore Majorana predicted the existence of these fermions. And then after that, he went on a trip with a boat and disappeared. And there's a mystery around this person. People don't know if he jumped off the boat or if he went somewhere else. And so there's a lot of theories about that too. But his theory on the fermions has now been used for quantum technologies. And the ingredients for this is that you need to have a nanowire device. This is a normal conductor that you have here. Here you have a semiconductor. And if you put a superconductor close to the semiconductor, you will create these special states, which are the Majorana fermions, which is the Majorana fermion is a particle. It's the particle and the antiparticle at the same time. It's very mysterious as Mr. Majorana. And it exists in a one-dimensional way, and it's delocalized here, and the particle is in one extreme and the antiparticle in the other. So you need a 1D wire, and you need to have the superconductor here. So you need a very high-quality semiconductor made in a 1D way. That's why we started working on this. So for this, we wanted to use this principle. We make the substrate in a way that we put the anti-sticking surface, the oxide, and we made slits to get the nanowires only grow there. It's not that easy. We want very high quality. So what we do is the following trick. So we do this, and we learn what the crystal wants to do, because there's crystal facets, there's crystallography, and you cannot just make a round shape, because as you've seen in the museums, geological museums, the crystals want to have several facets that are very well determined. So we look at what these facets would be for gallium arsenide, and these are the facets that have the lowest energy. And so when you have the orientation of the substrate and the openings, this gives you that if you make slits in all these directions, you will have only few that have vertical facets and that are a single crystal, not have defects. And this is then the equivalent of 1, 1, minus 2. And there are 3 of these in 1, 1, 1 substrates. So this allows us to make these these tripods here that are made of gallium arsenide. Now, gallium arsenide is not the material we want, and I will tell you later on why. But it is the base to create something on top. So the idea we had is that we have the gallium arsenide, and then we change the atoms. We add indium and arsenic. And indium arsenide and gallium arsenide have a lattice constant that is very different. So indium arsenide doesn't want to grow on gallium arsenide, really doesn't want to, because it stretches him, and they don't want to be stretched. So if you try to put it on top, it will not go here on the oxide, because this is not sticking. So we will try to do something here. And the prediction we had is that it will try to go at the tip, because that's the minimum contact surface, and it will create a 1D wire. And it will follow the nice crystalline structure of the base. And for once, this time it happened, so it worked right away. This is very rare in experimental physics. And so you see here in a cross-section, you have the gallium arsenide base, and you have here indium that is localized at the top. And you can see here from the top in a scanning electron microscope, you have a nanowire that really is positioned at the top. And this is the base for these Majorana fermion devices that we wanted to work on. So why indium arsenide? First, because it has very high electron mobility, and electron mobility means that the electrons, if you look at electrons in a metal, and you put a voltage, they will go from one side to the other, but in between, they will hit each other very often. And if you do this, then they lose coherence. And what we want is that the electrons stay coherent as long as possible. So you want to avoid these collisions, and for this one measure to do that is the mobility. This characterizes how many collisions will happen. And when you have very high mobility, if you do things well, you have ballistic transport, and so electrons behave as the photons in ray optics. And this is, of course, this is super cool, but that's also what we need to create these 1D wires. The second thing is that you need a material that has spin-orbit coupling, and this is typically materials that have very large masses, which means that there is a coupling between the magnetic moment and the momentum that the electrons have, which means that the momentum is how you accelerate with electric field, for example. It means that you can modify the position of the spin of the electron with an electric field. This is really cool, and if you want to do quantum technologies, you want to have this handle to manipulate the spins with an electric field. So that's why we use indium arsenide and not gallium arsenide. Now these wires, if we don't do anything, they don't conduct. They, as we saw in the last talk, semiconductors, you dope them by putting, silicon, you add phosphorus or boron, and it has 1 electron more and 1 electron less. So you need to dope them. When you do this, you change the mobility, and then you increase the collision. So it doesn't work. So what we did is we dope, we make a trick that is not ours, has been used for many long time, you dope the base where the gallium arsenide is, and then create electrons that want to go here because this is a lower potential, lower band gap, and so they all will accumulate here without having the dopant. So the dopants stay here. If you would have electronic transport here, it would perturb, but as they go here, you can have, in principle, the highest mobility of indium arsenide without having to dope the indium arsenide. So we did this. And then we made a device in collaboration with our colleagues in Basel, where we made the transport through this junction, so really the most difficult case. And we do this, we see a phenomenon as a function of the magnetic field, which is called weak antolocalization. And this is a sign that you have interference between the electrons that have along the path with different spin. And this tells us that we start having coherent transport, so we are going towards the way of having these electrons that behave more like ray optics than like electrons in a metal. You can see here that the mean free path is 300 nanometers or 20 nanometers, depending how we model the curve. And a spin orbit length is 80 nanometers, which is the length that you need to change the orientation of the spin. So it means that we can start to have a handle on the orientation of the spin with electric field. So this was good. And so the dream was that now we would have these 1D wires that we would couple to superconductors and create these Majorana fermions. But then something happened. So there were many groups in the world that were racing to have this, and in particular, the group in Microsoft. And I explain you this so that you know that science is not just we all have success and it's all very easy. It is hard, and it's part of the game, but also sometimes there are things that are less beautiful. And this is this. So you see here something happened with this paper, and many other papers happened the same thing. In fact, these papers on Majorana fermions, many of them, the most important ones, had to be retracted. And they were retracted because people were picking. I mean, the claims of why it's retracted is because some scientists that were part of this article were picking out some data points, taking them out because they were not fitting the theory they wanted. This is, of course, something you cannot do. And so, and that's why when you publish a paper now, everybody has to put the raw data in there, and that's what happened. Some scientists, they said, it doesn't make sense what they published. This doesn't work like this. I cannot reproduce their experiments. They asked for the raw data, and they saw that there were some, in the paper, there were data points that have been taken out to fit in the theory. So that's the story. And then we stopped working on Majorana fermions, even though it's a good experiment to do, and that the papers are retracted doesn't mean you cannot demonstrate it, but we just stopped working on this field. So then what can we do with 1D wires? So then we had a new project, and there's a very big project in Switzerland that is called SPIN, just to realize a quantum computing with qubits that are made of spins. And that's what I'm going to talk about now. So here you also have a 1D wire, and I will explain to you later how to do it. You put some electrodes to create a quantum dot here that has a single electron, and you control the spin of this electron that is here, and this is a qubit. If you are able to do this, you can scale up and have a race of nanowires with all their spins, and then you can start to think about a computer architecture with spin qubits. That's the idea behind this. The first person that thought about using germanium, so this is a different material, germanium as a material for spin qubits, was Charles Lieber in Harvard. And it goes like this. So here you have the valence band, the conduction band, and you have germanium with a silicon shell. If you do this, the way the bands align are in a way that you will have always lack of electrons here, so you will have holes. These are positive charges in the nanowire. So you have here the germanium wire covered with silicon. And you have it for free, you don't have to dope. So these are materials that can have very high mobility and so coherence, and so they are perfect for quantum applications. When you have freestanding wires like hairs, you need to put them on a substrate to put the contacts. This is really difficult. So it's much better if you can have them grown already on the substrate, as I showed you before, and then you can put the contacts as you like. So I would like to tell you a bit more how you define a qubit in a nanowire. So you have one of these nanowires, and this was where one of them, it's a different material, but it's one of them that you can take freestanding and put it on a substrate. And this is all very small, so it's complicated. You put some electrodes below, and with the electrodes, you elevate the potential in different regions. when you do this, if you look at the potential for the electrons, you see it's like mountains. And they like to be in the more lower states. As it's very small, there are quantized states, so they cannot occupy all the states, so you have them here. And you can already see that you can play many tricks, and here you can see that if this spin up is here, so the next one would like to be here, but if this is up, as there is only one state here, you will not be able to put this electron here because it can only go if it goes spin down. So here, this case here, you will be able to pass the electron around. So you can play with this, and this is an example of how you can use these electrodes here to create this potential landscape to play with the single electrons. So why do we want to have these standing nanowires? There's an additional reason for that. We can grow our germanium nanowires in selective area, but we can also engineer the shape. And the shape has an additional advantage. In fact, by choosing the crystal structure, the shape, and what kind of directions we're using, we choose the crystal asymmetry. And this allows us to play with this spin-orbit interaction that I told you before. And if with this, with the electric fields, you can annihilate the noise of the magnetic moments that you have in the atoms themselves. And this means that you can use, you don't need to use pure germanium, or people use germanium that is isotopically poor, that doesn't have a magnetic moment in the nucleus. With this, you just play with the shape, with an electric field, and you don't need to purify your germanium. You don't need to ask to Russian mines to give you this purified germanium. So how we do this? So at the same thing, we looked at the orientation dependence, and we grew this time with MOCVD, the germanium in selected areas. And this is what we wanted to have, this shape. And this is the first materials we do. So they were a bit longer than we wanted, but you see that in the tip they're single crystalline. So we have very high quality. We can also make these networks as we had before, which is necessary for having some logic. What we did is we created hall bars. So a hall bar is you have here a single wire, and you make some legs, some arms, so that then you can measure the potential also in these arms. And you measure the current that happens here, and you apply a magnetic field. And as you know, because of the Lorentz force, you apply a magnetic field, you have an electron going here, and you have a magnetic field. It will go on one side or on the other, depending if it's a positive or a negative charge. And this allows you to measure first what kind of charge there is, but also the mobility, and so characterize if you have coherent transport or not. So we did this, and we measured the mobility. We have about 400 centimeters squared per volt second, which is not very high, but it's, that is higher, but that's very high for a nanowire. And we identified that we have holes, positive charges, and that's the one that we want to have for the spin qubits. It has to be holes. This measurement here that you see is the conductance as a function of magnetic field. And you see, as we lower the temperature, we have a peak. And we also see you have a lot of oscillations. These oscillations are perfectly reproducible. And they are not noise, because they're perfectly distributed. They're above the noise level of the ohm meter. And in fact, they are due to interference that happens in the electrons. So they have the two contacts, and the electrons can go back and forth. They're delocalized, and because they're delocalized, there is interference as you have with the waves in the water. And so this interference gives rise to positive, negative interference, and that's why you have these oscillations here. And it's the proof that we are having also coherent transport with these nanowires. So this is the first step towards defining then these quantum dots. Here we have a phase coherence length of 100 nanometers, and we're improving it now with new structures. So how to improve? And so here is the thing. If you want to do very cool physics, you can only do it if you have very cool materials. So the initial wires I showed you were defect-free at the top, but we had some dislocations here. So we had to get rid of the dislocations, so we had to pay some tricks. If I look here, we made very thick oxide because we were thinking that the dislocations would get oxide, a defect. That's why we mask here. But why don't we try a very thin mask and play with the temperature, see if we just get rid of the dislocation by just cooking them and allowing the atoms to achieve the more relaxed state. When we do this, so here you don't even see the oxide, and we play with the temperature, you see that we have something at the interface, but we have the whole wire that is much smaller and defect-free. So playing with the materials, we are able to obtain very, very high-quality materials. Now, just to get a bit into the mind of material science, how we are able to understand what the atoms do, I show you a very small experiment. We go over this is the selective area, this is where they grow, and this is the mask, the anti-sticking mask, and we look at what happens little by little. So typically we would think that the atoms arrive and they just create terraces and they grow, but we saw that they create islands. This is not very good. You would think that would give low quality. So when they create the islands, they start to merge, and at some point they create a continuous wire. If we treat the surface in a different way, in fact, if we don't treat the surface, we also have these islands, and they don't merge. And you see, you don't need to know a lot to think that this will not give you a good material. So this is just by treating the surface in a different way before we start sending the atoms for the growth. So everything is very delicate, and it depends a lot how we do the nanofabrication and everything. So these are the ones that give the very good results on the transport. So now if we look at the second topic, I'll talk about energy harvesting and how we can get new materials that will help us have solar cells that are going to be much cheaper than what we have today. So I've shown you this pessimistic graph on how we are starting to emit CO2 and how this is going to result in that the temperature is going to increase a lot, and it's going to be very hard for all of us. It's not only the temperature, it's the climate that's going to become very unstable, and this implies everything. If the winter behaves like summer and the summer behaves like winter, it's very difficult to have fruit, it's very difficult to have crops, and if there are no crops, we cannot eat. So you can imagine how much the perturbation is going to be for all of us. But this person here, Jean-Dor, is an investor, and he thought he can do something else. So something like 12 years ago, he was an investor, very rich, very, very rich in California. And his daughter told him, yeah, Dad, but very good what you do, but you do nothing for humanity. Why tiny daughter saying, I don't respect you, you have a lot of money, but you could do something better. And in fact, this kicked him the interest, and from that day on, he only invested in companies that do something good for all of us. And in particular, he invested a lot in companies that produce green energy. And with all this experience, he decided to put a plan in a book. And if you read this book, it says, with the current politicians and policies, this is what's going to happen with the emissions of CO2. We're not going to diminish. And so he, with his speed and scale plan, he shows what we can do, all of us, to achieve the net zero in 2050. And it's not rocket science. It's things that we all can do. And we all have different qualities. And if you read this, there's all the parts that he puts, but basically he puts all that can be done for that. On our side, we try to contribute to decarbonizing the grid and also in innovation. And I think as a physicist, we're very good at innovation and solving problems, and this is what in our lab try to do. So if you look at solar cells and you look at photovoltaic efficiencies, you would see that it's the current that you can get and the voltage you can get. There is kind of a selection. So you have materials that are bad and materials that are very good. You see gallium arsenide is very good. You see crystalline silicon is very good at collecting a lot of current and less good at the voltage. And if you want to collect power, power is current times voltage. So you want high voltage and high power in your photovoltaic device. You also have other materials like aluminum phosphide. This is what is in the satellites and others here. Can we do better than gallium arsenide? We should, because gallium and indium are scarce elements. If we would all produce gallium arsenide solar cells, they would only be solar cells for the rich because they're super expensive and there's not enough of it. So we need to find an alternative. So can we create a material that is equivalent, but that is much more abundant? That is the question we started with. So you can look at materials that exist or that we know that could exist because we know the band structures. This is a list of materials, and this is an old graph because it's from 2009, but it tells you, given the efficiency that a material would have, what would be the amount of electricity you would create with the annual production that you have of this material, or the elements that compose the material. And you have also the annual needs of electricity in terawatt from the world. And yes, so you see that you have iron sulfide, you have copper oxide. These are materials that you all probably don't know. And there is zinc phosphide. And I'll tell you later on why I chose zinc phosphide to replace silicon. You have here amorphous silicon, and crystalline silicon is here. So it's below. It's worse than these ones here. You can look at another graph that tells you what is the material extraction cost index and the potential for producing electricity. So you want to create a new material that serves, you need to make sure that it doesn't cost much the extraction, and it has the potential to have high efficiency. So you have the crystalline silicon is here at the middle. You have gallium arsenide here, and you have zinc phosphide that is here. So we decided to work on zinc phosphide for this reason, but there was very little literature on this. Some people had attempted this material in the 60s and 70s, but there was really very little. So what we knew is that this material is a direct backup in the region that it should have for photovoltaics. It has a good absorption coefficient, and it has a thermal expansion coefficient that is very different from any material. So if you grow it on a substrate, you will have cracks. It has a tetragonal structure, which means it's difficult to grow on anything. In epitaxy, to create high-quality crystals, we try to mimic. We have the new material on top and mimics the structure below. And so if you have a crystalline structure that is very different, you will end up creating strain and defects. So the question is, how can we overcome this lattice matching need? Before going into this is the machine we use. So this is a molecular beam epitaxy. This is how it looks like. It's an ultra-high vacuum. You have the cells below, and we evaporate the materials. We don't evaporate phosphorus directly because it's very dangerous. We evolve the phosphorus from gallium phosphide. Like this, we avoid having a pot of phosphorus here that if something goes wrong, you create a fire right away and you kill the whole building. So we just have gallium phosphide that we let evaporate very controllably in the machine phosphorus. So a way to avoid this is you can restrict the growth in a very small area. In nanotechnology, you start growing in a very small area, and like this, you create tension at the beginning because the structure doesn't match quite, but it's very small, and then the material can expand and become its own. So you start small, and then it becomes bigger. Another thing you can do is you can just avoid having any covalent bond with the substrate. You just grow, for example, on van der Waals materials like graphene. And so the new material doesn't have to mimic anything because there is no covalent bond. And these are the two strategies we use for that. To grow on graphene, we use a commercial substrate from a Spanish company, Grafenia. They're in the Basque Country, and they sell you very big substrates with graphene on top. And you can just use this. You can buy it, and it's always the same, so it lets us do the experiment. So when we start this, there is a problem if we want to grow on graphene. There is no covalent bond with the substrate, which means that the atoms arrive, they have nowhere to stick. So this can be a problem, because they arrive, and they move around, but there is nothing to skid, so they can evaporate again. But thanks God, these materials are not perfect. So you have the graphene has polycrystalline, so have some grain boundaries and some point defects. So the crystal starts, the material starts to solidify in these grain boundaries and then grows laterally. And this is how it looks like. You see the crystals decorating the defects of the graphene, the crystal boundaries, and then you grow them. And some of them are oriented in the same direction. When they merge, they create a thin film. And this is an example of a thin film. So there is some bubbliness because of the graphene, but you see that you can create a thin film there that has very high quality. The idea here is that you have it directly on an electrode. Graphene is very conductive. You can create another electrode on top and then use the zinc phosphide as an absorber. Or because it's on graphene, it doesn't stick very well, you can just put it somewhere else that it sticks and remove the graphene. This is very easy because of the lack of covalent bonds. And you can put it on a substrate and maybe it's a better electrode and create your device. You can do it on plastic. You have many design flexibilities for this. So the other approach that is much better is you use the nanoscale approach. You start making, again, a mask where the atoms don't stick, and you start growing inside. And then you let the material create. The strain dissipates, and then it starts creating what it wants, so these facets and a pyramid. And then if the pyramids are close together, you will create a material that is a thin film that is structured like this. And so you use the nanoscale to nucleate. It dissipates the strain, and then you create a thin film that is with very few defects. If you look at the cross-section of this thin film, you will see there is some grain boundaries here, but the rest is purely single crystalline. And so this is a trick that we have made. If you would grow directly on the substrate without these nanoscale openings, you would be full of defects. If we look at the luminescence of the zinc phosphide, we see the room temperature luminescence, and this means that we illuminate with a high energy laser, and we get the laser to recombine and emit the band gap energy. Having luminescence is the key to know that it's a high quality material. So this was the first step to know that we're on the good path. We then created a solar cell. So we still use indium phosphide as a substrate because it's the one that matches better the structure. We put the zinc phosphide, we create, there should be a whole selective layer to discriminate the carriers that go on the other side. You saw in the Beyoncé talk that you separate the carriers, and in the diodes, they recombine to create light, and here the light separates them. So you need to separate them, and here is a kind of a guard that doesn't let the electrons go in. The electrons will have to go here, and the host will go here. So we created this device, and this is an example with the zinc phosphide. We put the indium tin oxide with a transparent electrode. It's a material that conducts, but it's transparent. We put some metal to extract the current, and then we measure. And what you see here, this current voltage that you see is typical of a diode. When we illuminate, we create some extra current. And this is the proof that we're creating power. This was the first device we did. It's a 4.4% efficiency, which for the first devices, this is something quite exceptional. This is the response. These are the wavelengths that are absorbed by our device and show that we're having really a functional device to start with. To do better, we should have between the ITO and the zinc phosphide, we should have really a material that only lets pass the holes. And we didn't have this at the beginning. If we do this, we should be able to increase the current and also the tension that we have here. So this is what we're working on now. We're working with a team in the Netherlands, Amolf, and we are working towards having this device to improve the efficiency. So hopefully I was not too long. I have convinced you that using nanotechnology, you can use the principles to create new materials, structures in the symmetry you want, to either use them for quantum technologies or to create new materials that enable a very efficient absorption for solar cells. And this is hopefully in the years to come make products that will help us to collect better the sunlight. All this work I didn't do myself. I have the chance to work with fantastic students. You see some of them here. The ones that I presented today are the ones here. They do a fantastic work. Also a lot of collaborators around the world. And this is part of the fun in doing science, that you work in a team, you work together. You're not alone in the lab, absolutely sad doing something. You really, of course, you do things alone, and you are independent of what you do, but you are collaborating and exchanging with a lot of people, and you rely on each other. And for me, this is the most fun part of science, and that's what I enjoy the most. And these people here are amazing, and so I need to thank them as well. Thank you.
Muchas gracias, Ana. Ahora vamos a comenzar la ronda de preguntas.
Well, thank you, Anna. Very interesting. I wanted to ask you, why are you interested in working on zinc phosphide instead of iron sulfide? Because on the slide about the extraction cost versus energy production potential or something like that, the slide, it seems to exceed the zinc phosphide.
That's a very good question. And we didn't select the iron sulfide because iron likes to oxidize very easy. You see it in the Teide. All the rocks are made from iron, and they're red because they oxidize. And iron really has a tendency to oxidize that is very strong, so it's very difficult to create this high-quality iron sulfide. And so far, the quality is so bad that I think the best efficiency is probably 0.1% because of this tendency of the iron to oxidize.
Any other, ¿alguna otra pregunta?
I was wondering, what is the timeline to make this kind of research appear in real life, and how commercially viable it will be?
So I have to answer. So for us to get the zinc phosphide to work, it took 3 years. So we were 3 years, 4 PhD students working for this, and no results. You have to believe a lot in yourself, and me as a supervisor to tell them, you are doing everything right, it's going to work, right? Then at some point it works, and it's very rewarding, but the years where there is nothing, it's very, very hard. So that's the first thing. And so it's very important to, if you do the things right with science, is that things at the end work because you are using the right technique. So that's the first thing. For the product, what we see is at the end, it depends a lot on how much people are able to collect investment to make it work. Because at the end, that is what's limiting. We need to progress still. We have an European project also with different partners. So at the end of the project, if we demonstrate a cell that is above 10%, above 12%, we will have the ingredients to maybe think about starting a small company. And then if there is enough investment, then one can think about in 10 years. But it all depends a lot on how many people can work on it, how much investment there is. Of course, on how good the idea is. So at the end of the project, we'll see if it's a good idea or not. If we see some roadblocker, then we'll do something else.
¿Alguna última pregunta?